In this video, we're going to continue our discussions of strain and measures of strain. We didn't talk about the elongation, but the elongation would be kind of the opposite of shortening, where we've got some initial length and the final length is actually greater than the initial length. And the shortening, the converse is true. We have the final length is shorter than the initial length. And in the example that we looked at, the length shortening was associated with folding. So there are different ways to look at this, but we have the elongation delta L over L sub I, or the shortening delta L over L sub I. Delta L would be less than 1 for the, or would be smaller than the initial length for shortening, and would be larger than the it would be negative for the shortening case and positive for the elongation case. And we would usually look at the absolute value of the delta L over L to say if there was 30% shortening as we had in the previous example rather than minus 30% length change. So this is our delta L, L sub I minus L sub F, and we have these two common measures that I'm sure you're familiar with. And now we also have something called the stretch, and the stretch is just the ratio of L sub F over the final length over the initial length, and so it would also be equal to 1 plus the elongation, referred to as the stretch. And here you can see where we're just kind of working with this definition for the elongation. It's L sub F minus L sub I over L sub I. And we can add 1 to the elongation, which we can represent as L sub I over L sub I. That's 1. Plus L sub F minus L sub I over L sub I. And so the L sub i's cancel out in the in the numerator, and we end up with an L sub F over L sub I, which is our stretch. So in the previous example, we calculated the length of the upper shallow fold. That turned out to be 13.34 kilofeet. And so that 13.34 kilofeet would be our L sub I, and the L sub F would be 10.26 kilofeet, which would give you a negative elongation. So the stretch is calculated above. If we just compare the final length, to the initial length, would be 0.77. So values of stretch less than 1 indicate contraction. And we also, you probably encountered this in your structural geology class, but there's a quantity referred to as the total natural strain, epsilon, and that's basically the sum of an infinite number of infinitesimally small extensions. And in order to get the total natural strain, you have to go through an integration process. So this might be a way you look at a really, really long-term process, ongoing for millions of years, let's say. And so here we have L sub I to L sub F over delta L over delta L or dl over L, which gives us the integral of dl over L is the natural log of L, and this is a definite integral, so we're evaluating from the initial to the final lengths, and so that we get this is equal to the natural log of the final length minus the natural log of the initial length, or the log of the ratio, which I think you'll recognize as the log of the stretch. Okay, we're going to kind of pop off on a tangent here for a minute and just talk about series approximations for this term, just to kind of bring back in some things we talked about earlier on. So we have the elongation defined as the stretch minus 1, or the stretch is equal to 1 plus the elongation. And we also have that the total natural strain is the natural log of the stretch, natural log of S, which would be equal to the natural log of 1 plus E. Now when we have something like this where E is a number less than 1, we can express this as an infinite series, the log of 1 plus E. Epsilon then would be equal to epsilon, the total natural strain here, equal to natural log of 1 plus E. We could calculate that as the elongation minus e squared over 2 plus e cubed over 3 minus e cubed over e to the fourth over 4 and so on. Just an infinite series of terms. And this might be something that you would do, that a calculator, the way that a calculator might go about doing it inside in terms of the electronics, or you could do this with an Excel file, which I did here. So we have our elongation, we have the total natural strain, 1 plus E. We're estimating the total natural strain as a series, but obviously we aren't going to calculate an infinite number of terms, so we just calculate out 6 places just to provide an example of how well the approximation, the six-term approximation, coincides with the exact computation obtained from the natural log. So we do pretty well at 5 decimal places with 6 terms. These would have been the terms that were used to get this number. So just remember that in a pinch you can make approximations using 2 or 3 terms of an infinite series. And if E is really small, then we can see that the log of 1 plus E is basically going to be pretty close to E. So these kinds of approximations come in handy. Now if we look at a table of numbers here and bring these numbers into Excel, we've got time steps going from 1 to 20. We've got strain increments of 5% with an initial length of 10% for all calculations. Final lengths, change in lengths, the elongation, and the total natural strain. And so what we plotted up over here is the elongation and the total natural strain. Now notice that the total natural strain increases linearly, and we'll show why that is in a minute, whereas the elongation increases exponentially. So if we take a look at the final lengths, for example, and we can fit an exponential function, the final length in terms of the initial length, times the base e to the 0.09531 times the time step. So this is an exponential function. Whereas the strain, is computed relative to the length in the preceding step, and the incremental strain is constant, and so we have a exponential growth in the total length, but the natural log is a linear relationship. And so if we take a look at the natural log of these lengths up here, the final length is equal to the initial length times e to the 0.09531. Take the log of f, the log of L sub f, and we see that we get a straight line. The natural log of the initial length plus 0.09531t. So the slope of this line here is 0.09531 times the time step, just the log of the stretch. So we do have that logarithmic or that linear relationship when we're looking at it in a logarithmic form. An exponential relationship when we're looking at it just in terms of the lengths, but when we look at it in terms of the logarithms, we have a linear relationship, the total natural strain, and I think you can see where we have about 1.9 divided by 20, we have this slope of 0.09531. So The elongation then, or the total natural strain, the log of the ratio, or the log of the stretch, is linear related to the time step. So just wanted to spend a little bit of time going over these different measures of strain, kind of tie that back in with our discussions of shortening with that fault propagation fold and so on. So we do get into an additional integral there with the total natural strain. And the next thing that we're going to do is take a look at volumes of revolution, volumes of cones and volcanoes, and we'll take a look at Mount Fuji and see what its volume might be. So, see you next time.